One wall of mountains that stretches across some of the most punishing, most hostile, most geologically violent terrain on the surface of this planet. And, yeah, $300 billion committed to punching through all of it. Right now, as you watch this, thousands of workers are deep inside the Himalayas, the Hengduan Ranges, and the Qinling Mountains. They are drilling through rock so hot it can reach temperatures above 50 degrees Celsius. They are building through ground that shifts between solid concrete in winter and unstable mud in summer. They are working at altitudes where the air contains only half the oxygen your lungs are pulling in right now. Altitudes where simply doing a full day's work requires supplemental oxygen just to stay functional. One tunnel they are building is longer than the entire island of Manhattan. One section of track will sit so high above sea level that commercial aircraft cruise at barely double its altitude, and one stretch of railway, just 133 kilometers of completed track, took 14 years to finish. Not 14 months, 14 years. To put the total price tag in perspective, $300 billion could fund NASA's entire Artemis moon program more than 6 times over. It could build roughly 15 Burj Khalifa skyscrapers every single year for a decade. It is more than the annual GDP of many mid-sized nations. China chose to spend it on mountains. And there is a very precise, very deliberate, and very consequential reason why. Welcome to Frontline Reports. I'm Nico. By the year 2030, trains will be moving through terrain that the engineering world once considered physically impossible to cross. When that happens, the trade map, the travel map, and the geopolitical map of Asia will shift in ways that are difficult to fully overstate. Entire regions that have been economically isolated for centuries will be connected to global markets. Alternative trade corridors between China, Central Asia, South Asia, and Europe will open that no naval blockade, no weather event, and no geopolitical crisis can shut down. This is the story of how China is spending $300 billion to rewrite the rules of what is physically possible, and why the mountains it is drilling through matter far more than most people realize. To understand why China is doing this, you need to look at a map of the country with fresh eyes. Because what that map reveals is something that shapes the entire strategic logic behind this $300 billion investment. China is, in a very real sense, two completely different countries sitting side by side, divided by geology as much as by geography. The eastern half of China is one of the most densely connected, most thoroughly networked societies in the world. Cities like Shenzhen, Shanghai, and Beijing are linked by an extraordinary high-speed rail network, the largest in the world, where passengers board a train in the morning and arrive in cities hundreds of kilometers away before lunch. The trains run at 350 kilometers per hour. The stations are modern, efficient, and serviced by dozens of departures every day. The infrastructure is world-class by any measure, and it has transformed daily life and economic activity across the eastern third of the country. Then go west. Go toward Tibet, toward Xinjiang, toward Yunnan. And the picture changes completely, abruptly, and dramatically. The mountains take over. And with the mountains comes isolation of a kind that is almost impossible to fully appreciate if you have only experienced the connected, modern, high-speed eastern half of the country. Communities that are separated by just a few hundred kilometers on a map can take 2 full days to reach by road, on routes that wind through treacherous mountain passes, cross rivers on narrow bridges, and disappear entirely in winter under snow that can accumulate for months. A truck carrying goods from a mining operation in western China to a factory in the east might spend an entire week simply navigating the mountain terrain between them. Roads that are passable in summer become impassable death traps in winter. Landslides close routes without warning. Seasonal flooding washes away sections that took months to repair. And in the harshest winter conditions, some routes simply vanish under snow and ice until spring. This is not just an inconvenience for the people who live there. It is a massive, ongoing, structural drag on the economy of a part of China that holds some of the country's most valuable and most urgently needed natural resources. Because under those mountains, under all that hostile, inaccessible, punishing terrain, sits something that China's growing economy desperately needs: coal, copper, and lithium. Lithium is the metal that powers the electric vehicle revolution, the batteries in every EV, every smartphone, every renewable energy storage system. China is racing to dominate that industry globally, and the raw material it needs to do so sits in significant quantities in regions that are currently extraordinarily difficult and expensive to access. Moving a ton of lithium from a Western Chinese mine to an Eastern factory costs far more than it should, not because of market pricing, but simply because the transport infrastructure to carry it efficiently does not yet exist. The roads are slow, unreliable, and expensive. The railways needed to replace them haven't been built yet. So the resources sit, partially stranded, in mountains that guard them jealously. There is also a strategic calculation running beneath the economic one that is, harder to quantify, but no less important to Beijing's planners. The world's busiest and most critical trade routes run through oceans, through ports, through narrow sea passages, the Strait of Malacca, the Suez Canal, the Strait of Hormuz, that represent choke points where the flow of global commerce can be disrupted, blocked, or leveraged by whoever controls access to them. A single container ship lodged sideways in the Suez Canal can hold up global trade for days. A naval confrontation in the South China Sea can threaten the shipping lanes through which an enormous proportion of Chinese imports and exports flow. China has been thinking very seriously about what happens if those sea routes are threatened, cut off, slowed, or simply made unreliable in a world that is growing, frankly, more geopolitically turbulent by the year. The answer Beijing's planners keep returning to is the same: land. Build enough railways through enough mountains, and you create trade corridors that no navy can block, no weather event can close, and no single geopolitical flashpoint can shut down. Land routes across Central Asia don't care about what happens in the South China Sea. A freight train running from Xinjiang to Uzbekistan is not vulnerable to disruption by a naval standoff in the Pacific. So these 7 railways are not, at their core, passenger projects. They are strategic infrastructure, designed to move coal, copper, lithium, agricultural products, manufactured goods, and international cargo along corridors that are, honestly, fundamentally more resilient than any ocean route running through narrow sea passages. Understanding that changes how you look at every single one of these projects. If you asked an engineer to design a route specifically engineered to be as difficult as possible to build a railway through, they would probably come up with something that looks a lot like the Sichuan-Tibet Railway. The workers and engineers who have spent years on this project have given it a nickname. They call it a geological museum. And that name, when you understand what it means, is one of the most darkly accurate descriptions in the history of infrastructure development. A geological museum means the ground does everything possible to stop you from building on it. Every geological hazard that exists, extreme heat, rock instability, tectonic activity, altitude challenges, permafrost, is present somewhere along this route. Sometimes multiple hazards are present at the same time, in the same location, simultaneously making construction more difficult in more ways than most engineers encounter in an entire career. The basic facts of this project are staggering in themselves. The total cost is $47.8 billion. The route stretches over 1,800 kilometers from Chengdu to Lhasa, connecting 2 cities that are currently separated by more than 40 hours of road travel through some of the most extreme terrain in the country. But the most astonishing engineering reality of this project is what happens on one specific section: the stretch between the cities of Ya'an and Linzi. On this section, 95.8% of the entire route runs either through a tunnel bored inside a mountain or across a bridge elevated above a valley floor. Just 4.2% of the track sits on open ground in the conventional way most people picture a railway. Think about that for a moment. For almost the entirety of this section's length, the train will never actually travel across the surface of the Earth. It will be buried inside mountains or hovering above valleys. The ground, quite literally, is not usable for most of the journey. The elevation changes along the full route compound the challenge. The track climbs and descends a combined total of 14,000 meters across the length of the line. That is roughly equivalent to stacking 2 complete Mount Everests on top of each other, and then doing it repeatedly across the entire route. Inside the tunnels, conditions that workers must endure go far beyond what most people would consider tolerable, let alone safe. Temperatures inside the rock can exceed 50 degrees Celsius, hotter than most domestic ovens set to a medium cooking temperature. Workers drilling through rock at those temperatures are doing some of the most physically demanding work that exists in the construction industry anywhere in the world. But the heat, severe as it is not even the most dangerous condition workers face. That distinction belongs to a phenomenon called a rock burst. Rock bursts occur when the pressure that has been building inside a mountain over geological timescales, pressure created by the weight of millions of tons of rock above by tectonic forces operating over millions of years, is suddenly released by drilling, blasting, or tunneling activity that removes the material containing it. When that pressure finds a release point, it does not escape gradually. It explodes outward, violently and without warning, sending razor-sharp fragments of rock flying in every direction like shrapnel from a detonation. This is not a controlled demolition. It is the mountain's uncontrolled response to being cut open. And it is a condition that workers on the Sichuan-Tibet Railway have had to develop entirely new safety protocols to manage. Protocols that did not fully exist before this project began because no previous project had encountered this particular combination of hazards at this scale. As of early 2026, tunnel construction on the line is approximately 75% complete. The full route is targeted to open by 2030. The timeline itself tells the story of the difficulty: 14 years of work to complete just 133 kilometers of track in the most challenging sections. 133 kilometers. That is roughly the distance from one side of a large metropolitan area to the other. It took longer to build than some countries have taken to construct entire national highway systems from scratch. When the line eventually opens, it will reduce travel time between Chengdu and Lhasa from over 40 hours by road to approximately 13 hours by rail. That single change, 40 hours to 13, will transform the economic and social connectivity of Western China in ways that will compound over decades. Engineers are, by nature and by training, precise people. They don't hand out superlatives carelessly. When the engineering community designates something as the hardest, the most difficult, or the most extreme, those designations are based on measurable, documented, quantifiable evidence. Which is why it matters that the Dali-Ruli Railway in Yunnan Province has been officially designated as the most difficult railway ever built anywhere on Earth. The basic dimensions of this project sound manageable enough on paper. The total length is 330 kilometers. Shorter than many of the other projects in this program. On flat cooperative terrain, a railway of that length would typically take about 3 years to build from initial construction to final opening. The first completed section of this line, from Dali to Baoshan, took 14 years, not 3, 14. When you understand what workers encountered underground during those 14 years, that timeline stops being surprising and starts being remarkable that it wasn't even longer. The critical challenge comes down to a single tunnel, the Zholigang Mountain Tunnel, which at 34.5 kilometers is the longest mountain rail tunnel in all of Asia. That length alone would make it an extraordinary engineering achievement. But the conditions inside during construction turned it into something far beyond an ordinary engineering challenge. During the tunneling process, workers struck massive underground water flows that had not been fully anticipated in pre-construction surveys. This was not a matter of encountering some moisture in the rock, or dealing with the gradual seepage that is a normal part of tunnel construction. The scale of what they found was something else entirely. The total volume of water that flooded into the tunnel during the construction period was equivalent to approximately 156,000 standard Olympic-sized swimming pools. 156,000 swimming pools worth of water, forcing its way through the rock from every direction simultaneously, while workers were trying to construct a precision-engineered railway tunnel to within millimeters of specification. Imagine trying to build something that requires absolute geometric precision, using heavy machinery, in a space that is simultaneously filling with water coming from sources you cannot fully predict or control. That is approximately what workers on the Gaoligong Mountain Tunnel faced for years. And the water was not the only challenge. The Hengduan mountain range, through which this tunnel was bored, sits in one of the most geologically active zones anywhere on the planet. The tectonic plates beneath this region are in constant, slow, and occasionally violent motion. The rock layers run in directions that are difficult to predict or model in advance. Temperatures inside the tunnel fluctuate in ways that damage and degrade equipment faster than replacement parts can be sourced and installed. Every kilometer of progress demanded a level of creative, real-time problem-solving that simply has no equivalent in standard railway construction practice anywhere in the world. The final section of the line, from Baoshan to Ruili, remains under construction and is expected to open in 2028. At that point, this project will have been under active construction for approximately 20 years. 20 years for 330 kilometers of railway. That is the cost of these mountains. Not just in money, though the financial cost is enormous, but in time. In years of human effort, engineering ingenuity, and physical endurance applied to terrain that resisted every step of the process. But when the line opens, it will accomplish something that no road, no existing route, and no previous infrastructure investment has managed. It will give China and Myanmar a direct, all-weather, reliable rail connection through terrain that currently makes surface travel between the two countries genuinely grueling, for trade, for tourism, for ordinary people trying to move between these neighboring nations without spending days on roads that close in bad weather and disintegrate in the monsoon. That transformation, slow in the building, immediate in the impact, is exactly what the entire $300 billion program is designed to deliver. If the Sichuan-Tibet Railway is expensive and the Dali-Ruli Railway is the hardest ever built, then the Xinjiang-Tibet Railway exists in a category of its own. A project so extreme in its operating environment that no meaningful comparison with any other railway in history fully captures what it represents. The price tag is $56.2 billion, making it the most expensive individual project in the program. But the number that defines this railway is not financial. It is altitudinal. The line stretches nearly 2,000 kilometers from Hotan in Xinjiang all the way to Lhasa in Tibet. And across almost the entire length of that route, the track runs at an average elevation of more than 4,500 meters above sea level. To put that in context, most commercial passenger aircraft cruise at around 10,000 meters altitude. This railway operates at nearly half that height, and it does so not at a single high point, like a mountain pass that you cross and descend from, but as the sustained, continuous operating altitude for almost the entire 2,000-kilometer route. At 4,500 meters, the atmosphere contains approximately half the oxygen available at sea level. This is not an environment where the human body functions normally. Construction workers cannot simply arrive on site and begin their shifts. They require supplemental oxygen just to perform basic tasks. The kind of work that would be completely routine at lower altitudes becomes genuinely taxing and potentially dangerous when your body is operating with half its normal oxygen supply. Equipment behaves differently too. Internal combustion engines lose significant power output at high altitude because the thin air provides less oxygen for combustion. Simple mechanical operations take longer. Even cognitive tasks, the planning, the calculation, the decision-making that construction requires, are affected by the physiological stress of working at altitude for extended periods. But the altitude, extraordinary as it is not actually the most challenging engineering problem on this route. That distinction belongs to permafrost. Approximately 61% of the Xinjiang-Tibet Railway's route crosses terrain underlain by permafrost, ground that freezes solid in winter and partially thaws in summer. This seasonal cycle of freezing and thawing creates one of the most difficult substrates for railway construction that exists anywhere on Earth. In winter, the frozen ground appears stable and solid. Track laid on it seems secure and level. But as temperatures rise in spring and summer, the ice within the soil melts, and the ground loses structural integrity. It becomes soft, unstable, and prone to settling unevenly. Track that was perfectly aligned and leveled in January can be warped, cracked, sunken, or heaved by July. For an ordinary road, this kind of seasonal movement is manageable. You repair the surface damage and move on. For a high-speed railway, where track alignment must be maintained to tolerances measured in millimeters and where deviations can cause derailments at operating speeds, seasonal ground movement across 1,200 kilometers of route is an engineering problem of an entirely different order of magnitude. Engineers working on this project are developing solutions that have no real precedent in railway construction. Foundation systems designed to thermally isolate the track structure from the ground below it. Monitoring systems that can detect and respond to ground movement before it reaches the threshold where it affects safe operations. Track designs that can accommodate a defined range of substrate movement without compromising structural integrity. These are not refinements of existing techniques. They are new answers to a problem that existing railway engineering has never been asked to solve at this scale. Despite all of this, the project is moving forward. In 2025, a dedicated management entity, the Xinjiang-Tibet Railway Company, was established with over $13 billion in startup capital specifically to oversee the construction and eventual operation of this line. Active construction began in 2026. The full route is expected to be operational sometime in the mid-2030s. When it opens, the strategic implications are substantial. The railway will unlock Xinjiang's massive coal reserves by providing reliable, high-capacity transport from mines to processing facilities and onward to markets. It will create a permanent, all-weather land corridor connecting two of China's most strategically important but physically isolated regions. And it will extend China's unbroken rail network into some of the most remote and previously inaccessible terrain anywhere on the continent. The 5 projects we have discussed so far are all, in various ways, about connecting China's internal geography, linking the isolated West to the connected East, opening access to resources, and reducing the travel times between Chinese cities that are currently separated by extreme terrain. This next project is different in a fundamental way, because this one crosses international borders. The China-Kyrgyzstan-Uzbekistan Railway is, at 523 kilometers total, shorter than most of the projects in this program. But in terms of geopolitical significance, in terms of what it does to the map of global trade, it may be the most consequential line of the entire $300 billion investment. To understand why, you need to understand the problem it solves. Right now, if you want to move cargo from China to the Middle East or Europe, your options are limited and imperfect. You can ship by sea, which means weeks in transit, enormous vessels navigating through the Suez Canal, and exposure to every choke point and disruption that global maritime shipping involves. Or you can use existing overland routes, which are slow, fragmented, frequently interrupted, and nowhere near capable of handling the volumes of freight that serious continental trade requires. Neither option is satisfactory. Both involve either time costs or reliability costs, or both simultaneously. And both are vulnerable to exactly the kind of geopolitical disruptions that make Beijing nervous about its trade security. The China-Kyrgyzstan-Uzbekistan Railway changes the calculation entirely by providing a direct, high-capacity, all-weather rail connection from China through Central Asia, a connection that bypasses the maritime choke points entirely. Construction officially launched in December 2024 with a ceremony in Jalalabad, Kyrgyzstan, a moment that was more symbolic than most international rail groundbreakings because it represented the formalization of an agreement that had been in negotiation for decades. The full line runs 523 kilometers, connecting Kashgar in China's Xinjiang province to Andijan in Uzbekistan, cutting directly through Kyrgyzstan's rugged mountain interior. The terrain is challenging. Approximately 40% of the entire route is comprised of bridges and tunnels. 50 bridges and 29 tunnels covering 120 kilometers of the most difficult sections. The engineering work required is substantial, though it does not reach the extremes of altitude or geological hazard that characterize the purely domestic Chinese projects. The financing structure is revealing in its own right. The total cost is $4.7 billion. China is providing half of that amount as a 35-year concessional loan, and China holds 51% ownership of the joint venture that will build and operate the railway. For Kyrgyzstan and Uzbekistan, countries that could not individually fund infrastructure of this scale, the arrangement provides transformational connectivity that would otherwise be decades away if it arrived at all. For China, it represents a direct, tangible investment in a faster, more reliable, more resilient path to the markets of Central Asia, the Middle East, and Europe. The payoff, once the line is operating, is